Hi students, here we're going to take a look at sketching graphs of rational functions. When we're dealing with rational functions, the very first thing we need to do is understand what causes some of the behaviors. And the biggest thing that we have to worry about are things that cause our rational functions, things that are fractions, to be undefined. That would be any time that we would be caused to divide by 0. So if we can't divide by 0, anything that would cause the denominator to be 0, we cannot use for an x. So what we do is we set this up and we solve this. I can factor this, so we got x minus 2 and x plus 2 are the values that we know cannot be 0. That tells me that x minus 2 cannot be 0, which means x cannot be 2, and x plus 2 cannot be 0, which means that x cannot be 2, negative 2. These are our domain restrictions. These are the values that are undefined for this particular rational expression. What we're really doing when we're finding undefined things is looking for vertical asymptotes. And the key to this is always going to be factoring things. When we are trying to find vertical asymptotes, we're looking for undefined values that don't cancel out. We're going to talk a little bit more about that in a few minutes. So if I take a look at my terms here, we're going to do some factoring. I'm going to start by factoring the bottom. I can take a 2 out of all 3 pieces to make this a little bit nicer. X squared minus 5x plus 6. And that's going to end up as 2 times the quantity of x minus 2 and x minus 3. That means that x cannot equal 2 and x cannot equal 3. Those are my undefined terms. I've also got to factor the top of this and see if either one of those cancel out. So let's take a look at this. We've got a times c is 48x squared. B is going to be negative 14x. Things that multiply to negative 48x squared. Well, I've got to have negative ones. Negative 148 doesn't work. Negative 2 times negative 24. Nope. Negative 3 times negative 16. Now we're really close. Negative 4 times negative 12. No. Negative 5 doesn't work. Negative 6 times negative 8. Hey, that gets me to negative 14. Okay. So 3x squared minus 6x minus 8x plus 16. I can take a 3x out of both of those, leave me with an x minus 2. And I can take a minus 8 out of both of those, leave me with an x minus 2. 3x minus 8 and x minus 2. So here's why we go through all of this trouble. We're going to build a fraction here. So f of x is going to be equal to, and on top we have 3x minus 8. We've got x minus 2. On the bottom, we've got 2 times x minus 2 times x minus 3. As we look at this, you might notice that x minus 2 is on the top and the bottom. We said that vertical asymptotes happen when we have undefined values that don't cancel out. When they do cancel out, this creates a hole in the graph. We're going to see some more of that in a few minutes. For this particular problem, we're looking for vertical asymptotes. The only factor left in the bottom is x minus 3. That means our undefined term for x cannot equal 3 is our vertical asymptote. So x equals 2 as a whole, x equals 3 is a vertical asymptote that I'm going to abbreviate VA. Horizontal asymptotes we find quite differently. Horizontal asymptotes are based on end behavior of a graph. What happens as x approaches infinity or as x approaches negative infinity? One way for us to kind of think about this is what happens to our equations as x gets really, really, really big. And one of the things that happens, let's say we plug 1,000,000 into this. We basically have 2 times 1,000,000, because 1,000,000 minus 1 is basically 1,000,000, over 1,000,000. And if we have 2,000,000 over 1,000,000, we end up with 2-ish as our answer. In fact, if you got even bigger, let's talk about 1,000,000,000,000. It's going to be so close to 2 it doesn't even matter. So what we say for this is that our horizontal asymptote is going to be at y is equal to 2. We tend to have 3 cases if we're looking at horizontal asymptotes. Those are cases that come out to be undefined. Those are cases that come out to be 0, and those are cases that come out to be a number like we see here. When each of those pop up, we're going to talk about those a little bit. All right, all horizontal asymptotes for the following function. I'm going to use the same type of thing we did in the last slide. I'm going to talk about plugging in a really, really big number. I'm not going to start as big as I did last time, but I would like us to notice is that even if you plug in, I don't know, like 100, 200 plus 2 is basically 200. Here we've got 100 squared. That's 10,000. So we'd have like 3 times 10,000 and then minus 100 minus 4. That's basically still 3 times 10,000. What I'd like you to notice is that when the denominator has a higher degree, that's going to get much bigger much faster. So we're dividing a small number by a huge number. And if you keep following this out, we're going to get closer and closer and closer to 0, so that my horizontal asymptote would actually be at 0. This is going to happen every time that the degree on the bottom is larger than the degree on the top. All right, next up we're finding some x-intercepts. X-intercepts happen when y is equal to 0. We do have to be a little bit careful with these because we might accidentally get some x-intercepts that can't exist, and I think that's what's going to happen here, which is annoying. I didn't mean for that to happen. You know what? I'm going to change the bottom of this to 3x plus 3 so we don't have to worry about it. We're good. So x-intercepts, we're worried about the top. I just got to make sure that those don't interfere with our domain. So we know that 3x plus 3 cannot equal 0. That means that x cannot equal negative 1. For x-intercepts, we're going to set the whole thing equal to 0. And one of the things I'd like you to notice is that we can very quickly multiply by the denominator. And when we do that, we end up with 0 is equal to x squared minus 2x plus 1, which by golly looks factorable. This is going to factor into x minus 1 times x minus 1. That gives me an x-intercept of x equals 1. By the way, if we had left that as 3x minus 3, we would have ended up canceling out one of our terms, which means that would be a hole in our graph. Find all the holes. Hey, we just talked about that in this function. So we said that holes exist if we cancel something out. So the first thing I'm going to do is decide what can't work here. This is going to factor into x minus 8 and x plus 6. That means we have x equals 8 and x equals negative 6 as excluded values. All right, next thing I'm going to do is factor the top of this. I'm going to take a 2 out, and we get x plus 6. I notice I've got an x plus 6 on the top and the bottom. That's going to cause a hole in our graph. X plus 6 equals 0 is a value that would be a hole. So we end up with, sorry, I'm messing up my notation here. X equals negative 6 is going to be a hole. Now we're going to put things all together. We've got to try to identify all the features all together. And we're going to work kind of in order for this. So horizontal asymptote, we know that's based on the top and the bottom together. Here I've got the degree is squared, so we've got a degree of 2, a degree of 1 on top. That means we're going to bring it down to 0 because the larger bottom of this is going to pull it down to 0 instead of letting it equal out at something else. For a vertical asymptote, I'm going to start off by identifying values we can't use. That's based on the denominator. And I've got to be a little bit careful before calling these true vertical asymptotes. So I've got x squared plus 4 is equal to 0. That means that x squared is going to be 4 and x is going to be plus or minus 2. Okay, I'm going to hold off on vertical asymptotes for now. And I'm going to look at the top of this, and I'm going to factor that into 2 times x plus 2. That's interesting, because that's one of the things I just got from the bottom here. The minus 2 means that this should be x plus 2. What if I took a negative out here and wrote this as x squared minus 4? Then that factor's a lot nicer for us. That's going to be x plus 2 and x minus 2. The x plus 2's are going to cancel out. By the way, that's going to be my hole. So x equals negative 2 is the hole in my graph. And to figure out what the y value is, we plug it back into our equation. 2 times negative 2 is negative 4, and then we get, oh, that's interesting. Oh, no, that's where we get the 0. Oh, that's a mess. I'm going to wait till I reduce this. And change my color just so we can deal with this. All right, there's my sort of messy thing that I made. My x plus 2's canceled out. I've got a 2 on top. I've got a negative, and I've got an x minus 2 on the bottom. Okay, now I'm going to plug my hole into here and see what happens. We've got 2 over negative 2 minus 2 is negative 4. That makes it positive. 2 over 4 is going to be a half. All right, x-intercepts. Well, now we have no way to make the top 0. So there are none. And then y-intercepts, I'm going to plug 0 in for x. We end up with 2 over 2. That gives us 1 as our y-intercept. And then finally back to vertical asymptote. We had 2 values that we could not use. We got x cannot equal 2 or negative 2. Negative 2 was a hole. That means the positive 2 one is going to be a vertical asymptote. The graph of this, so we've got a vertical asymptote at 2, which we draw as a dotted line. Horizontal asymptote at 0. A y-intercept at 1. And we've got a hole in the graph at negative 2, comma a half. So it's going to be like 1, 2. And I accidentally filled that in because why not? That's really what I wanted. Is negative 2 comma a half. Nice smooth curve connecting those, my rational graph basic shape. And we're going to have an opposite hyperbola in the bottom corner. Same thing with messier numbers. Let's start out by factoring the top and the bottom. We figured that that's a really useful thing. I can take a negative 3 out, and I've got x squared minus 25, so that's going to be x plus 5. and x minus 5. On the bottom, I can take a 5 out. That would leave me with x squared plus 7x plus 10. That's going to be x plus 5 and x plus 2. My excluded values, I'm going to call x vals, are going to be x cannot equal negative 5 and x cannot equal negative 2. Now I'm going to cancel some stuff out. And this makes it a lot easier for me to work with. My hole in the graph is going to be caused by x equals negative 5. Horizontal asymptote. Let's rewrite this. We get x minus 5 over 5 times the quantity x plus 2. If I plug a really big number in, the negative 5 and the plus 2 really don't matter. We end up with, like, I don't know, negative 3 million over 5 million. So my horizontal asymptote would be like negative 3 over 5. For a vertical asymptote, that's going to happen when the denominator equals 0. So 5 times x plus 2 cannot be equal to 0. That gives me x equals negative 2 as a vertical asymptote. For the x-intercept, the shortcut for this is looking just at the numerator. And we end up with negative 3 times x minus 5 is equal to 0. That means that x equals 5 is going to be an x-intercept. And then for a y-intercept, we're going to plug 0 in for x. We end up with negative 3 times negative 5 over 5 times 2. Negative 15 over 10 is negative 1.5. And then finally, I got to plug negative 5 into my equation here to figure out what the y value for the hole is. We got negative 3 times negative 10 over 5 times negative 3. It's positive 30 over negative 15, negative 2. All right, we're going to do the same exact thing, but now we're going to graph this beauty. I'm going to start by factoring things so we can begin this process. We're going to factor the top, take a negative 4 out, we get x plus 3. On the bottom, things that multiply to negative 6 and add up to 5. That's going to be 2x and something and 1x and something. I want this to be minus 1 and plus 3, which also makes sense based on this problem because we're going to end up with a hole. So we got negative 3, we got negative a half, positive a half. X plus 3's cancel out. There's my hole. And I might as well just plug that in right now. So we've got negative 4 over negative 6 minus 1 is negative 7. Oof. Negative 3 comma 4/7 is going to be 4/7. There we go. Okay. Next up, let's do my vertical asymptote. 2x minus 1 cannot be 0, so we get x cannot be a half from that. My x-intercept. There's nothing left on top, so there's none. That's kind of weird. We skipped my horizontal asymptote. I'm having a feeling that's going to tell us why we have no x-intercept. The bottom of this is bigger, therefore y equals 0. That's why we do not have a horizontal asymptote. I'm sorry, that's why we don't have an x-intercept, because the horizontal asymptote is on the x-axis. And then a y-intercept. Plugging in 0, we get negative 4 over negative 1 equals 4. Nice smooth curve. another one to match it. And we are good. Using the homework software, it's going to do the graphing part for you as long as you identify the pieces correctly.